Now that we understand something about the process model, let's take a closer look at rework. So when we think about rework, it has to be in the context of the product, the nature of the product, the processes involved with the product, and the materials. So let's look at some specific examples. Here we have a set of glass bottles that are being produced. The question is, what happens when we have scrap? So when scrap occurs through our process model, we have to make a decision whether or not we're going to be successful at rework. If we're going to be successful, R should be close to 1. If we're not going to be successful, R will be close to 0, and therefore there's really no need to attempt a rework on that particular component. If R is equal to 1, then it might be worthwhile to do some rework and bring it back to the original value. Now in the case of glass, we might have chips and flaws in the glass bottle, and in order to rework that bottle, we would essentially have to melt it down to its original state and then place it in the mold again. And therefore, it would indicate that our rework, or a chance of rework, is equal to 0, because essentially we are returning to the initial state, which is the raw material going into the mold. And in that case, it would not make sense to do any rework, and so all of this scrap, if any of these bottles represent scrap, would enter the waste stream. Now that waste stream might be recycled in terms of going back to the original mixture and being added to new glass. Let's look at a different product. Here we've got a wedding cake. And what happens when this is detected as being scrap? Well, we have to think about the nature of the product. Can it be reworked? Well, it really depends in this case upon the nature of the flaw. So if we have some type of flaw in the surface here representing the frosting, then you might agree that R will approach 1 and could potentially be reworked. If, however, the contents of one of these layers is bad in terms of what if the baker mistakenly put salt instead of sugar, that would be a major problem. And in terms of recreating that, rework may not be possible, and so we would create an entire new layer and then rework the entire assembly based upon this layer that we've recreated. So in that case, R would approach 0 for that specific layer, but for the entire product, R would be somewhere between 1 and 0. Let's look at another product. Here we have a cast product, very large, and the question is, what happens when we have scrap? Well, in this case, the product is so large in terms of the amount of material that it would suggest, no matter what the condition, we would want to rework this product, and it also suggests that R will approach 1. In terms of what will happen during rework, we may be adding material to various parts of the geometry. We may be removing material and then adding material in order to produce the final characteristics of the product. But it's highly likely in this case, versus if we were to scrap this product, then essentially we're returning it to its initial state, and we've lost a major investment in terms of energy and the processing that went into that component. Here we have a set of tablets produced by a pharmaceutical company. The question is, if we do not have enough of the active ingredient in this product, then it would be considered scrap by the FDA. In other words, it does not have the necessary dosage in order to make it effective. So is it possible to rework this product? Well, it depends, again, on the ability to return this product to a state where we could add additional active ingredient or add additional excipients, in other words, the other material besides the active ingredient, and get the right mixture and then press it again into a tablet. So this would involve grinding the material into a powdered mixture and then doing some additional mixing and then again forming the tablet through a press operation. So there is some potential here, but it will likely be somewhere between 1 and 0. Here we've got a circuit board with various components on here. The question is, what is the likelihood of performing rework? Well, it depends on the nature of the scrap. If the scrap has to do with the internals of the circuit board, in other words, we've got some bad layers in our pathways here, then that will be extremely problematic because it may involve going into layers of the circuit board that are not on the surface, and therefore that would be very difficult. R, in that case, would approach 0. However, if the defect is due to an incorrect component or the failure of a component, then we can remove that component quite easily and replace it, and in that case, R would approach 1. So you can see two different kinds of defects that produce scrap can result in different outcomes. Here we have an assembly, and in the strut here we've got some seals. Oops. We have some seals, and we've got our rod here in the strut, and we're going to assemble this together into our final product. So what happens when we have scrap due to an incorrect assembly? Now, how could we have an incorrect assembly? Well, again, when you think of the individual components going into this product, what if the operator forgets to put this washer 17 into the assembly, or forgets one of our components here? Then we're going to have a defective product. So the question is, what is R? Now in this case with an assembly, if we detect that it is not functioning and therefore it's defective, we can disassemble it and then add the necessary components. In other words, replace them if they're defective or if they were not assembled in the first place. And so for an assembly, R tends to approach 1 because of this ability, in most cases, to be able to disassemble the product and then reassemble with the correct parts. Here we've got a forming operation where I am, again, creating certain product characteristics through a set of punch operations in terms of stamping. So you can see features in the side here, features in the top, that were created through stamping operations, and we're also doing some bending operations to create our edges here. So if we have a defect in this case, can we rework this product? Again, it depends upon the nature of the defect. For instance, if I have a problem with this stamping operation in terms of location, it may be impossible to repair that because we've already removed the material. However, if I have a problem with the geometry of an individual feature, I might be able to rework that individual feature and create the necessary geometry as long as it's in the right location. Or if my bending operation creates a bend at the wrong angle, I may be able to, again, rework that by going through that bending operation again and trying to create the correct angle. So the nature of R here will depend upon the defect that is produced in that particular process. Here I have a food product, and in terms of a defect, it could be based upon the contents of this box. It could be based on the amount of material that's placed in the box, so it is rated at a certain level. If we have insufficient material or too much material, we might consider that scrap. Or if the contents of the box are not at the correct mixture, again, we would want to remove that box and treat it as scrap. The question is, what is R in this case? Well, clearly, R in this case will depend upon the nature of the defect. If the box is sealed, then R will approach 0, unless we're willing to open the box, remove its contents, and of course the box itself would be scrap, and then we could fill a new box. But in most cases, for food products, R is going to approach 0. In other words, there's no chance of rework. So how do we incorporate this into our model in the sense of material balance that we talked about last time. In our material balance, we had question marks about how much material is moving to rework and how that ends up in our final process stream in terms of good product. So our goal is to achieve a certain level of value that's being added by the process. Our scrap rate, as we've said before, it will be the fraction of defective parts that are produced in our process, and that results in our material either going into the waste stream or entering rework, and then subsequently, if it's returned to the intended value, we will go to the next process in our system. If we look at the average number of parts reworked, it'll be based upon the fraction of parts that need to be reworked, which is S, right, our fraction of defective parts. So we multiply R, the probability of successfully reworking, times S. That gives us that average fraction of parts reworked, and if we are adding material, that's the amount of material that we would add on average. Of course, it will vary depending on the nature of the product. So now we can balance out the flow of materials here, and we can see here that R plays a major role in what we see going to the next process. So the quantity of material will be based upon R times S times Q, as we just saw, plus the material that we added. And a certain amount of material, 1 minus R times SQ, will enter the waste stream, and then that will have to be dealt with along with the original waste that was produced by the process. So now we have material balance when we consider rework. Well, let's look at producing the number of parts that are required by the customer. As we saw before, that will be based upon our scrap rate. So again, scrap rate is a critical parameter. Now we ask the same question. If I need N good parts coming out of this process, how much do I have to put into the process to produce that quantity? Well, that's going to be based upon our scrap rate. So 1 minus S times X will be the good parts. And then R times S minus X will be the bad parts that we will successfully rework. And then they'll be added to form N. So we end up with this quantity representing those good parts. And now all we have to do is use a little algebra and solve for X. So X turns out to be the number of parts we need to produce divided by 1 over 1 minus R times S. The meaning of that ratio, 1 over 1 minus R times S, is that for every good part, we need to make this quantity of parts. So if you look at this ratio, just like 1 over 1 minus S, it's strictly greater than or equal to 1. So if R is equal to 1, what's going to happen here is that this will reduce to 0. 0 times S will be 0, and so we'll produce exactly one good part. In other words, it'll be perfect in every case because we fully restored every part. If, however, R is equal to 0, then this will reduce to 1 over 1 minus S, which is what we had originally, and therefore rework has no effect, which makes sense because the likelihood of success is 0. Another aspect is the energy. In addition to the materials, we look at the processes and the energy required to transform that material. Depending on the nature of the equipment used in that transformation, will consume different amounts of energy, and as you know, energy is becoming increasingly important in the context of manufacturing because it will relate directly to our cost. We can see energy being used in electric motors that are used in air compressors, a major consumer of energy, pumps, machining processes. We have hydraulics, again, hydraulics driven by motors, heating and cooling, material treatments, welding operations, lasers, and you could continue to list others that are consuming energy to transform the material. If you look at the energy flow, again, in the same model, what we see is energy entering our process, and then some slight deviations in terms of energy from the external environment. We also see losses in the process, such as heat transfer and so forth. Once we create our part, and we're assuming they're good parts, we're going to have a certain amount of energy plus some question mark, and the question mark is coming from the rework. So if we look at parts that are bad, this scrap, we might have to consume additional energy. There may be some losses, and if it's good, then we're going to enter the stream to the next process. The amount of energy that was invested here, of course, could be less than E or greater than E, depending upon the amount of loss that we have during this process, the amount of loss here. Now, some interesting work was done by Professor Gutowski and some others, where they looked at a variety of processes, as you can see here. And on the X scale, we see the rate in terms of processing material. That's our material balance. And this is in volume of material per second. And then here we have the electricity requirements in terms of joules per centimeter cube. Again, volume that we're transforming. And it may be difficult to see this, but at the bottom here, a variety of common processes that are used to transform material. Now, the interesting thing is, as you can see here, this curve appears to be well behaved, primarily linear, and then it becomes asymptotic towards the end as the volume per second is increasing dramatically. Some of the processes that you should take note of, which are quite common: machining, injection molding. Again, if you look at machining, it's in this region down here, where the requirements are significantly reduced and we can produce large volumes of material per unit of time. This suggests that machining is, from an energy perspective, an efficient process. If we look at injection molding, again indicated by the square here, that is even more efficient. Again, much larger volume per second of material that we can produce, and the energy requirements are less than machining. At the other extreme, we see more costly processes. Again, processes such as oxidation. At the very top, where we're consuming a large amount of energy to produce the characteristics in the product, versus something like grinding, which is just above machining, again, more efficient, but not as efficient as machining. So this gives us a way of looking at what types of processes, if possible, should be used to reduce the energy requirements in our system. So some of the strategies we might have are, first of all, when we look at the processing equipment that's used in a specific process, how could we modify that in terms of any machine tools or molding that's involved to reduce energy consumption? One approach is convert any use of hydraulics to electric motors, and this could have a significant reduction in energy. The other criteria we might look at is the production rate, and with production rate we could increase the rate, again if you think of that in terms of the volume of material per unit time, by introducing those technologies that increase the rate of production in an efficient manner, as we saw in that graph. In addition to energy, we also have to consider timing in our processes. So if we look at our process model from a timing perspective, now we're concerned about the length of time to produce that part in terms of a good product. So when we think of our process, the term cycle time should come to mind. Again, that represents the amount of time to go through that entire process. The other time component would be any rework time that's required to restore it to a good product. What does that look like in terms of a time scale? Well, when we think about an individual process, we think about when a part arrives at the process And this occurs at this instant in time. And as you can see here, time is progressing from left to right. After some period of time, the processing actually begins. So this represents the actual cycle time. After the cycle time is complete, then there's a period of time before the part leaves the process. So you should have some questions at this point, and that is, what does this time correspond to? What does that time interval correspond to? And are you adding value 100% of the cycle time? Well, this initial time interval represents a period of time in which we're not able to process. And most likely, that's due to the fact that there's already a part that is being processed, and so we're going to have to wait some period of time. This time interval is most likely due to the fact that we cannot leave the process because we're waiting for space and or a material transfer device to go to the next process. And so we're going to end up waiting and waiting. And is there any value in doing that? Clearly not. So there's a significant portion of time spent waiting at an individual process. If you add all of that up, a significant portion of the time for an individual product is going to be non-value adding. Then if we look at the cycle time interval, we also note periods of time in which nothing is happening in terms of transforming the material, and that is primarily due to setup and removal of the part from the process. And so there's handling involved in which there is no value that's being added. The last perspective you should take in looking at a process is the amount of uncertainty in the process. And by uncertainty, we mean that there is variation in terms of that waiting time from process to process. In order to deal with uncertainty, what we're going to introduce are a set of buffers, as you can see here, that represent space in our system. So as uncertainty increases, we're going to have space allocated that is proportional to uncertainty. The greater the uncertainty, the larger amount of buffer we're going to need in each of these areas. So if I'm uncertain about when I'm going to move to the next process, then I'm going to increase the size of this buffer to allow greater variation, and so we'll build up some inventory of parts here that can move to the next process. The same concept here with the rework buffer if I have a lot of uncertainty with rework, which tends to be true, and with the process itself. So if there's a great deal of uncertainty for material arriving at the process, then I want to make sure, in order to keep this process utilized fully, that I have enough material here to make full use of that process. So all these different perspectives on a process give us an entire or a complete view of what is going on in that process. Again, the key concepts that we've covered here are rework. When can you do rework? The timing involved in terms of a part arriving, when it leaves, and what happens in between. Uncertainty due to when parts and material arrive at a process and when they can leave a process. So in summary, the ability to perform rework, as we've seen, is highly dependent on the nature of the product, both in terms of how it was processed and in terms of its geometry. Energy usage should also be considered when you're selecting or improving processes. And we saw in the work done by Kutkowski that there is a relationship between production rate and energy and which processes are more efficient. As the uncertainty of your process is going to increase, the amount of storage at a particular process will by necessity have to increase as well.